Welcome back after the break. This week we have two papers that are kind of like last week's papers about fuzzing, but I want to say they're more like testing papers. And so let's talk about them specifically. So the first paper I'm going to describe is MonkeyDB. And so the idea here is that we want to test applications that do things on key value stores and databases. And normally you think, well, you put something in and then it's there and then you request it and you get the same thing back. But when you have distributed storage, that's no longer the case. And so it's like, well, can we make sure that our program behaves as we want? Or at least can we test for the failure modes that are likely to happen when you relax the consistency constraints that you normally expect on single server data stores, right? And so what they do is implement this way of testing on databases that are not as consistent as you want. So you basically generate executions that are going to test the assumptions on sequential consistency and find errors with your program. And so they have a number of tests starting from micro benchmarks through to well-known test suites, and find that their approach does find consistency errors under weak consistency assumptions on these benchmarks. Okay. The second paper is about compilers. And so again, it's kind of like fuzzing, but kind of not. And so here the idea is that we want to test compilers. And the way you want to do that is you want to feed code to compilers and see what happens. And so, well, either the compiler crashes, and that's easy, or it miscompiles, and that's not so easy. In any case, the point is compilers usually fail with complicated programs. And if you give a complicated input program to the compiler writer, they're like, I don't know, this is too complicated. Why are you giving me a program with 5,000 lines and telling me to find the bug? They're like, forget about that. And so what they want to do is they want to find simple compiler errors. And how do you do that? Well, the way they do that is they use semantics performing transformations, which is not a new idea. But then I guess their main contribution is they're like, okay, to generate our programs, we're going to use this set of transformations. And here's some good principles for designing the set of complications such that you get errors that are easy to, you get programs to feed to the compilers that are easy to compare to correct programs. And well, if you do this transformation, then you're going to exercise the thing. And furthermore, if you use these rules for making transformations, then it also is the case that you can then distinguish between different root causes of the programs that you transformed. And that's super helpful because, well, you ran your program or your 100 programs, and 50 of them report errors. And so you're going to submit 50 errors to the compiler. Well, that's probably not going to go over well. If you submit 50 errors and they're different, that's fine, but it's probably not. It's probably 3 errors that are different and 47 duplicates. And so they use the transformations to classify which errors are likely to be clustered together. And so they said, test case reduction and deduplication almost for free with transformation-based testing. The other part of it is the reduction part. So if you design your transformations to find compiler bugs following these rules, then you're likely to get reduction for fairly cheap. And then they evaluate how it works on Spear 5, I guess is what it's called, how it's read, and which is a GPU compiler, and find that it behaves how they want, and that it works better than the old fuzzing tool that was previously state-of-the-art. All right, so that's it for this week's papers, and I'm doing this early because I'm working on an eco paper. So tomorrow I am going to do nothing related to the course, and then I will see you on Wednesday after viewing the videos and commenting on them. See you then.